So we are going to talk about conservation of energy today, okay? Conservation of energy, and we've talked about, what we've looked at so far is that an object has kinetic energy if the object is in motion, right? So anytime you hear kinetic energy, you think motion, okay? And then the faster the object's going, the more kinetic energy it has. In other words, let's say a car driving 20 miles an hour is going to have less energy than a car driving 55 miles an energy, right? 55 miles an hour. The car going 55 miles an hour is going to have more energy, okay? And also, you can add to that the size of the vehicle. A fire truck is going to have more energy than a tricycle, right? Does that make sense? It's going to have more potential and kinetic energy, okay? Okay, so in order for an object kinetic energy to increase, it must get energy from somewhere. But where do we get that energy? Where do we get energy from? Anybody know? Well, think back to this roller coaster. What kind of energy did it have at the top of the hill? When the roller coaster is at the top of the hill, what kind of energy is that before it goes down? You know it's kinetic when it goes down, but when it's at the top of the hill, what kind of energy is that?
Potential.
It is potential energy. Okay, so in order for an object's kinetic energy to increase, it must take energy from its stored energy. So anytime Mr. Hughes says kinetic energy, you think motion, right? Anytime Mr. Hughes or anyone else actually talks about stored energy, think what kind of energy, Isaiah? What kind of energy? Potential energy. Yes, potential energy. Okay, so so in order for an object's kinetic energy to increase, it must take energy from its stored energy, which we call potential energy. Okay, so stored energy is potential energy. Kinetic energy is energy of motion, or it's motion, right? Okay, so when this happens, the potential energy that an object possesses decreases. Okay, just as when the roller coaster goes up the hill, it's losing kinetic energy and it's gaining potential energy, and at the very top, that's where it has its most kinetic energy. And then it starts back down, and its potential energy is decreasing, and its kinetic energy is increasing. Okay, until the car gets down to a certain point where it starts going back up the track or the hill, and then it starts gaining potential energy and losing kinetic energy. And it's just like a cycle, okay? Because even though the kinetic and potential energy are changing, the total energy is that in that closed system, or the TE, we call it TE, closed system does not change, and that's called it really should be called the law of conservation of energy, because that's one of those laws of physics, okay? So you have initial total energy, which is represented in a math problem as capital T, capital E, and then a little I, equals total energy, the final, okay? Okay, let's move on here. Okay, so when energy is conserved, when you think it's conserved, think that it's still there. It's just changing form. It's not created. It's not destroyed. So when energy is conserved, no energy is added or taken away from the system. The total energy you start with is the total energy you end with. It's just in a different form, either potential or kinetic, right? Or it could be chemical to electrical and so on. So in other words, energy cannot be created or destroyed, and that's the essence of the law. That's essentially what the law of conservation of energy says. It says energy cannot be created or destroyed. It can only be transferred or changed from one form to another. Okay, does that make sense? All right, we're going to move on here. Okay, so let's look at this conservation of energy a little bit closer here. So when looking at the mechanical energy of a system, you remember a mechanical energy has got to have moving parts, like the water turning the turbine on, like at a dam that creates electricity for a city or whatever, or region. So water going through the turbines turns the turbine. Okay, so when looking at the mechanical energy of a system, the total energy possible is the potential energy and the kinetic energy added together. So it becomes an addition problem, right? So there's math and science, right? We already know that. We've done several of them, right? So therefore, another way to write conservation of energy is this right here. Potential energy plus kinetic energy initial equals potential energy plus kinetic energy final. Okay? Let's look right here. So when would potential energy be zero? Well, the object is on the ground, or when a spring or other elastic material is not stretched or compressed. Okay? Look right here at the ball here. Okay, the ball is at rest right here on the counter. Okay? Those of you at home can't see it, but there's a ball at rest on the counter. That is zero potential energy. Okay? Okay. Okay, so when would kinetic energy be zero? The object's not moving. Okay, so look here. Here's here's kinetic energy. Is this object moving? It's going to stop in a minute. Okay. Okay, the object's not moving. Okay, that would be kinetic energy zero.
Do we write that down?
Huh?
Do we?
Nah. You don't have to write that down. No. Okay, let's look right here. Okay, so let's see if we can determine the total energy of a ball that is dropped from rest. Okay, rest. Okay, the figure below shows the ball at different positions as it falls. So starting with when it's at rest at 1 meter, here's its rest at 1 meter, before being dropped. So use the idea of a conservation of energy to determine the missing values, okay? So, and we're going to remember that the total mechanical energy at that position is a sum of two individual energies, potential energy plus kinetic energy, right? So we have total energy is 0.5, okay? Potential energy is 0.5. So what's our kinetic energy? Zero, right? Makes sense? Does that make sense? Yes. Okay, look right here. Okay, the height is 0.5 meters, half a meter. Here's a meter stick right here, so half of that meter stick. So it would be right at 50, that'd be a half a meter from here to here. Okay, let's look right here. Okay, so look here. So your total energy is 0.5 meters, and the potential energy, here it was 1 meter, here it's half, so it's going to be half and half, right? Like here's this 0.5, 0.5. There we go right here, half and half. What do you think this is going to be right here? Anybody want to take a guess? 0 meters, what do you think?
0.
0.5, 0 potential energy because it's at rest, right? And the kinetic energy is the same thing as the total energy. Okay, so let's move on. Does that make sense so far? Mm-hmm. Okay, so let's look right here. Here's our roller coaster. All these people look like they're happy, don't they? Okay, so let's look right here. So at position A, here's position A. At position A in the diagram below, the roller coaster car has 40 joules of total energy and has a velocity equal to 0 meters. That's at full potential energy, isn't it? Okay? So how much kinetic energy does the car possess at point A? How much kinetic energy? 0, right? Because it's at rest. It's at rest at point A. Everybody see that? At point A, it's going to have 0. So how much gravitational potential energy does it have?
0.
Huh? Anybody want to guess? Look right here. From here to here, 40 joules. That's how you figure that out. Okay? Got the idea? How much potential energy will they have down here? 15 joules. Okay, got the idea? How much potential energy do they have here?
25.
25. Okay, you got the idea. Okay. Okay, so now let's look right here. Woo! Okay, so at position B. Oh, did we just answer that question? What'd we say? At point B, 40 joules, right? We're talking about total energy and kinetic energy right here. 40 until they get right there. Okay, 40. And how much kinetic energy at point B? 25, because 25 minus 40 minus 15 is going to be what? 40 minus 15 is going to be what? 25, right? Makes sense. A little bit of addition, subtraction. Okay, so let's look right here. Okay, so at point C, we're right here, point C, okay? At point C in the diagram below, the roller coaster has a gravitational potential energy equal to 25 joules, right? Right up here at the very top, if this were right here, from here to here, that is the potential energy is 25 joules. So how much total energy does it have? 25 plus what? 15, right? 25 plus 15, 40. Okay, how much kinetic energy does it have at point C? 40 minus 25 is what? 15. Got the idea? Easy? Okay, so here's your question. Here's the question right here for you. Woo! Okay, this should be an easy one. Okay, so at what position in the diagram below does the object have only gravitational potential energy? Well, I'm going to help you out here. Is it W or X? W or X? Mark your answer. Okay, everybody got an answer? Look here, here's W up here. At what position in the diagram below does the object have only gravitational potential energy? Here's W, here's X. Does this have only potential energy down here at X? Mark your answer, W or X, A or B. Okay, look right here. At what position in the diagram does it have only kinetic energy? Would it be W or X?
You said the potential or kinetic?
Right here we're asking for kinetic energy. At number 36, we're asking for potential energy.
Okay.
Okay, so now this number 37 is kinetic energy. Would it be full? Would it have kinetic energy here or kinetic energy here at X? Mark your answer. Okay, let's look right here. At what point would it have both potential and kinetic? So mark your answer. There's more than one answer. Gravitational potential and kinetic. There's two answers there. Okay, mark your answer. Everybody got an answer? I'm gonna move on here. Okay, so let's look right here. We'll come back to those. We'll come back to take a look at our answers later, okay? We're not in any hurry about looking at answers right now. Our main point is we're trying to understand how we can mathematically determine the kinetic and potential energies, right? Okay, so the transfer of kinetic energy to potential energy. There's a transfer, right? So just as potential energy can be transferred to kinetic energy can be transferred into potential energy, okay? The total energy of the object must always be the same due to the conservation of energy, right? Because you can't create energy, you can't destroy energy. Are you okay with me, Daniel?
Mm-hmm.
Okay. You okay? Okay. All right. So the total energy of the object must always be the same due to the conservation of energy. So let's take a look at the ball that's dropped from 1 meter again. And we said the total energy is half, 0.5, and the potential energy is 0.5, and the kinetic energy is 0, right? Okay, because it's not moving anywhere. Look right here, and so the height is half a meter, and the total energy is, 0.5 joules, and the potential energy is 0.25 joules, or 1/4, and kinetic energy is the same, 0.25 joules. And then over here, look here, and this is what we said earlier, the total energy is 0.5 joules, potential energy is 0, and then the kinetic energy is the same, 0.5, because these two numbers always have to be the same. See, these two numbers, potential and kinetic, always have to be the same. Okay? Okay, look right here. Let's look. Okay, so, the kinetic energy at the bottom will be transferred to gravitational potential energy as the ball gains height, okay? So look here, I've got this ball again, and the higher I raise this ball, the less kinetic energy there is and the more potential energy there is, right? Okay? Okay, so, because of the conservation of energy, the total energy stays the same. So here we are, we're right back at these are the exact same numbers that we had earlier, right? Okay? Oh boy, what happened there? Okay, so let's look right here. So in reality, the ball will not bounce as high as it was dropped. Does this mean energy is lost? No. It just means that some of that kinetic energy that the ball had when it first hit the ground was transferred to the ground, listen, as heat and sound. When you have kinetic energy, there is heat and some sort of sound involved. Daniel, I need you to lift your head up. Sophia, lift your head up.
No, I got my screen.
I know, I want you to lift your head up because it makes me think you're sleeping. Okay, so again, in reality, the ball will not bounce as high as it was dropped. Does this mean that the energy is lost? No. It just means that some of the kinetic energy that the ball had when it first hit the ground was transferred to the ground as heat. There's a certain amount of heat and sound because, listen, do you hear anything? Did you hear anything? There's sound energy, right? So some of this kinetic energy was sound. You heard it. And also when something hits another object, there's a certain amount of heat. There's a certain amount of heat that's generated. Certain amount of heat. So some of that was changed from kinetic to potential, but also sound, because you heard the sound, right? And then heat, which you may not have. You could, if you had the right tools, you could measure the heat. Okay. Okay, so some of it, excuse me, some of it is lost to heat and sound. And neither of those, by the way, those are both non-mechanical energy, right? Heat and sound, because it doesn't take any object to create it. It's either waves. Okay, so if we consider the ball on the ground to be a closed system, then the system's total energy is the same. Now, I'm not going to bore you with these numbers again here, okay? Here we go. Okay, so let's talk a little bit about the transfer of kinetic energy to potential energy, okay? So kinetic energy can also be transferred to elastic potential energy. Look right here. What do you got right here? What are these? Springs, right? Okay, they're springs. So the conservation of energy still applies, which means the total energy remains constant. And so let's consider a system that is composed of a block and a string. Okay, here's your block, and here's your spring. Okay, so let's look at this. So in the top picture here, this picture right here, in the top picture, the block is traveling at 10 meters per second. You see that right here, right? 10 meters per second. Meaning that it has kinetic energy, right? Because it's traveling, it's moving. Anytime something's moving, it's got kinetic energy, right? Okay, so the spring is relaxed and therefore has no elastic potential energy. Okay, and the total energy of the block spring system is entirely due to the kinetic energy of the block right now, okay? Here's the block. Okay, and this is relaxed. Is it relaxed? Okay, what is it here? Is this relaxed here? No, it's compressed, isn't it? So let's look at that. So on the bottom picture, the block has compressed the spring and is no longer moving. Is it moving? Is any movement there? Nope, nope. Okay, so in the bottom picture, the block has compressed the spring and is no longer moving. The block has transferred its kinetic energy to elastic potential energy, right? So this thing compressed, it's got potential energy now, right? Does that make sense? Okay, so the total energy of the block spring system is entirely due to the elastic potential energy in the spring. Does that make sense? This is relaxed, there's no energy. This is compressed, there's energy, right? Potential energy. There's kinetic energy here. There's potential energy here. Okay? Woo! Okay, so let's look right here. So in which position of the block would the system have only